find out the molecular mass of a non-volatile solute from the depression of a freezing point. And the relation is this. You must write the relation. MB is equal to, write the equation. MB is equal to 1000 kF into WB by delta TF into WA. And that is the relation for molecular mass of the non-volatile solute. That is from the depression of a freezing point delta TF. Equation you are written, MB is equal to 1000 kF into WB by delta TF into WA. All right? Where, you write, where MB is equal to molar mass of the non-volatile solute, molar mass of solute, WB, mass of solute, that is in gram, mass of solute, that is in gram. WA, mass of solvent in gram, mass of solvent in gram, that is important. Mass of solvent in gram. And what else? KF is there. It is molar depression constant. Molar depression constant. Molar depression constant or a cryoscopic constant. And there is one more term, that is delta TF, that is depression of freezing point. Depression of freezing points of the solvent. So these are the terms. So using this equation, we can calculate molecular mass of a non-volatile solute from the depression of a freezing point. Okay. Solutes like say glucose, sucrose, urea, etc. can be calculated using this method. See in here, delta TF is the cryoscopic constant. I mean, this is the depression of freezing point. It is the democratic property or a colligative property. Let us try to solve a problem using these equations. Try to solve a problem. You write a problem. Write a problem. 45 gram of ethylene glycol, 44 gram of 45 gram of ethylene glycol, problem. That is it. 45 gram of ethylene glycol. You know the formula C2H6O2. 45 gram of ethylene glycol, C2H6O2. C2H6O2 is mixed with 600 gram of water. It is mixed with 600 gram of water. 45 gram of ethylene glycol, C2H6O2 is mixed with 600 gram of water. Calculate the freezing point depression. Calculate the freezing point depression. And freezing point of a solution. and freezing point of a solution. Freezing point of a solution. You are given Kf for water. Kf for water is equal to 1.86. 1.86 Kelvin kilogram per mole. These are the data given. 45 gram of ethylene glycol C2H6O2 is mixed with 600 gram of water. Then calculate the freezing point depression and freezing point of the solution. Kf of water is 1.86 Kelvin kilogram per mole. So what all things we have to find out? A freezing point depression and freezing point of a solution. There are two parts. Freezing point of the solution. Okay, let us think of the equations known to us. Which are the equations known to us? Freezing point, which are the equations? One is delta T F is equal to, Anna, you say delta T F is equal to, Anna, come on, louder. Delta T F is equal to, you give the equation. Still, I cannot hear you. What's the problem? Michael? Michael, delta TF is equal to, can you hear me or not?
Kf into M.
Formula delta TF is equal to, Punya, you say?
Kf into M.
That is one relation. Okay. Delta TF is equal to KF into M. That is one relation. Then delta TF is equal to, that is from the freezing points of the solution solvent. So
Tf0 minus Tf.
B 0, not B, it is F. It is F. Delta, see here, it is F. Very sorry. Okay. So T F0 minus TF. That is another equation. You have to find out what. You look at these equations and you say, Anna, what we have to find out? Only three equations you have studied. First one is this, delta TF is equal to TF0 minus TF. What is delta TF? What is delta TF in the equation? എൻ്റെ മോളെ എന്താ ഇപ്പൊ നോക്കിയിരിക്കണേ ഇവിടെ മനസ്സിലാകുന്നില്ലെങ്കിൽ അത് പറയണ്ടേ അതായിരിക്കും ഞാൻ എനിക്കറിയാം. What is Punya? What is delta TF?
Depression of freezing point.
That is a depression of a freezing point. അതല്ലേ ഒരു ക്വസ്റ്റ്യൻ? ഓക്കെ, അതല്ലേ ഒരു ക്വസ്റ്റ്യൻ? ഡെൽറ്റ ടി എഫ് അതാണ് ഒരു ക്വസ്റ്റ്യൻ. Say calculate the freezing point depression. Depression in the freezing point. Delta TF. അതാണ് ഒരു ക്വസ്റ്റ്യൻ. രണ്ടാമത്തെ ഏതാ? Freezing point of the solution. ഇതിൽ ഏതാ freezing point of the solution? അശ്വിൻ പറഞ്ഞേ. നന്ദന യൂസ് in the relation. ഇതിൽ ഏതാണ് freezing point of the solution?
Tf.
TF. അപ്പൊ എന്തൊക്കെയാ കണ്ടുപിടിക്കണ്ടേ? ഡെൽറ്റ ടി എഫ് കണ്ടുപിടിക്കണം. ടി എഫ് ഒന്നാമത്തെ അറിയണ്ടേ, എന്താ കണ്ടുപിടിക്കണമെന്ന് അറിയാണ്ട് എങ്ങനെയാ? ഒരാളൊരു ചോദ്യം ചോദിച്ച ചോദ്യം മനസ്സിലാക്കുക ആദ്യം. We must understand the question first. എന്നിട്ട് നമുക്ക് മറുപടി പറയാൻ പറ്റുള്ളൂ. ഈ freezing point we have studied only 3 equations. One is delta TF, that is a depression of freezing point. Freezing point depression, delta TF. Then TF0, freezing point of a pure solvent. TF, ഞാൻ അതുകൊണ്ടാണ് ഞാൻ പറഞ്ഞ ഞാൻ ഈ ക്ലാസ് എടുക്കാനില്ല എന്ന്. ശരി. So in the depression of freezing point, we have only 3 equations. One is for the molecular mass. അത് ഇവിടെ ചോദിച്ചിട്ടില്ല. And what are asked here are, one is the freezing point depression of freezing point, and it is delta TF. അതാണ് പറയുന്നത്. 2, freezing point of the solution, and it is TF. അതാണ് കണ്ടുപിടിക്കേണ്ടത്. അപ്പൊ TF കിട്ടണമെങ്കിൽ എന്ത് വേണം? TF കിട്ടണമെങ്കിൽ നമുക്ക് ഡെൽറ്റ TF കിട്ടണം. TF കിട്ടണമെങ്കിൽ we have to get a delta TF. TF0 is known to us. TF0, that is a boiling point of the solvent. Adriya, boiling point of the solvent, that is known to us. That is not given in the question, that I agree, but we must know that. What is it now?
Freezing point 0 degrees Celsius. 0 degrees Celsius.
0 degrees Celsius. 0 degrees Celsius. Okay. 273.15 Kelvin. Because it is water. The solvent is water. അത്രയെങ്കിലും സുബോധമില്ലാതെ കണ്ട് then why are you here in the class? That is not given in the problem, but we must know that it is water. 0 degrees Celsius. So the unit used should be Celsius, degree Celsius. Or you can write 273.15 Kelvin. Then you must write the unit Kelvin. Okay? അത് ഏത് വേണമെങ്കിലും ഉപയോഗിക്കാം. You can use both. There is no problem. So to get TF, we must know delta TF. Delta TF we get to use the second equation. So you write the equations known to you. You write the equations. Delta TF is equal to TF0 minus TF. TF0 minus TF. Second equation. Delta TF is equal to KF into M, molality. KF into M. Okay. So to get to delta TF, KF is given to us 1.86. That is given. But molality is not given. Molality is not given. We are given only some masses and some formula. Some masses and some formula are given to us. From that, we have to find out the molality. What is molality? Number of moles of solute per kilogram of the solvent. M is equal to molality. M is equal to moles of solute. The old equation from the beginning. Examination problems will be asked. Then you must know the relevant equations. Without knowing the equations, how can you solve the problem? Moles of solute by number of moles of solute per kilogram of the solvent. So mass of solvent in kilogram. Mass of a solvent in kilogram. Mass of solvent in kilogram. Okay. That is equal to moles of solute. Which is the solute here? Which is the solute?
Ethylene glycol.
Ethylene glycol. How will you get the number of moles? Number of moles. Mass by
Molar mass.
molar mass. What is the mass here? 45 by molar mass. You find out. അറിയില്ലെങ്കിൽ കണ്ടുപിടിക്കുക. C2H6O2. Carbon atomic mass 12 into 2 is equal to 24. Hydrogen atomic mass 1 into 6 is equal to 6. Oxygen 16 into 2 is equal to 32. Add it. What is the molecular mass? Come on, you say 62. 62. That is equal to 62. Molecular mass is 62. So 45 by 62. That is a number of moles of solute by mass of solvent in kilogram. What is mass of the solvent? 600 gram. So you convert that into kilogram. What you have to do, Emmanuel?
600 by 1000.
Correct. 600 by 1000. 600 by 1000. Simplify ചെയ്യണം കേട്ടോ. Simplify ചെയ്യും. We don't get more time here. So I shall do one thing. We shall do one thing to find out M, molality. Molality is equal to 1.2 moles per kilogram. It's equal to 1.2 mole per kilogram. That is the molality. You simplify it. Slowly you can simplify it. Not now. Please don't waste the time now. Okay. Have you got the method? Do you follow the method?
Yes,
That is what I want to know. So moles of solute, mass by molar mass. If you don't know the molar mass, you have to calculate using the molecular formula. So mass in gram by molar mass by mass of solvent in kilogram. Unfortunately, the mass of the solvent is given in gram. So you have to convert that into kilogram by dividing by 1000. So 600 by 1000. And the value that is equal to 1.2 mole per kilogram. Unit എഴുതുകയാണ് എങ്കിൽ so much mole per kilogram. അതെ എഴുതിയാലും കൊള്ളാം എഴുതിയില്ലെങ്കിലും കൊള്ളാം. 1.2. That is the molality. Now we have got the molality. If we get the molality, since Kf is given to us, we can calculate delta Tf. Therefore, delta Tf, that is the depression of freezing point, is equal to, we know the equation, Kf, Kf into M again is equal to 1.86 into 1.2. 1.2. Simplify ചെയ്യാൻ പറ്റുമോ നിങ്ങൾക്ക്? You try. On simplification, the value will be 2.2 degree. It may be Kelvin or degree Celsius, whatever it is. The difference in temperature 2.2 degree. If you put that in Kelvin, then freezing point of water should be in Kelvin. If you put this in degree Celsius, then freezing point of water should be 0 degrees Celsius. Okay. This is only the temperature difference. This is only temperature difference 2.2. That is the difference in the freezing point. Maybe Kelvin or degrees Celsius. That is left to your freedom. So we have got a delta Tf is equal to 2.2 degree. Okay. So one part is over. First part, freezing point depression. So freezing point depression, that's equal to 2.2 degree. Maybe Kelvin or a degree Celsius. Now, if we get the delta Tf, from that we can find out the freezing point of the solution. For that you make use of a okay. We know this relation. Delta TF is equal to, come on, TF 0 minus TF. Therefore, TF, that is the freezing point of the solution. You take that to the left-hand side and the delta TF to the right-hand side. So TF0 minus delta TF is equal to, you find it out. What is TF0, Emmanuel?
So solvent, sir.
Parai. Which is the solvent here?
TF0.
My dear, you just go through the question. In the question, it is given which is the solvent. Which is the solvent?
Ethylene glycol. Ethylene glycol.
Ethylene glycol is the solute. Solvent is water.
Water, sir.
Water. If it is water, what is the TF0? Freezing point of water?
0.
0 degrees Celsius. That should be very careful. You can use 0, no doubt. But you must write this degree Celsius. 0 degree Celsius minus. What is delta TF?
2.2.
2.2. That is equal to, Emmanuel, complete.
Minus 2.2.
Minus 2.2 matram parayale.
Degree
The
Celsius.
unit also.
Degree Celsius.
Degree Celsius. Degree Celsius. If you want to convert that into Kelvin, plus 273.
Plus 278.
273. 273 ചേർക്കണം. അപ്പോൾ നമുക്ക് we'll get Kelvin. കേട്ടോ വേണമെങ്കിൽ അപ്പോൾ എന്താ ചെയ്യുക ഇതേ കൂടെ മൈനസ് 2.2 plus 273.15 Kelvin. Kelvin ആക്കണമെങ്കിൽ കേട്ടോ അല്ലെങ്കിൽ ഡിഗ്രി സെൽഷ്യസ് രണ്ട് സൗകര്യം പോലെ ചെയ്യാൻ നിങ്ങൾക്ക് അത് സിംപ്ലിഫൈ ചെയ്യുമ്പോഴേ വാട്ട് വിൽ ബി ദ വാല്യൂ ഇഫ് ഇറ്റ് ഈസ് ഇൻ കെൽവിൻ 270.95 ശരിയല്ലേ ഇസ് ഇറ്റ് റൈറ്റ് 270.95 Kelvin ആണെങ്കിൽ or you can write in the unit degree Celsius. Okay. മനസ്സിലായോ? Or you can use instead of 0 degree Celsius, you can directly use 273.15 Kelvin minus മക്കളെ നോക്കിയേ ശരിയല്ലേ നോക്ക് 273.15 minus 2.2 അപ്പോൾ ശരിയല്ലേ but the unit is Kelvin. Do you follow the difference?
Yes, sir.
അപ്പോൾ അത് നോക്കിയിട്ട് വേണം യൂണിറ്റ് എഴുതാനായിട്ട്. You write one more problem you write 1 gram of 1 gram of a non-volatile electrolyte. 1 gram of problem number 2. 1 gram of a non-volatile solute. Non-volatile solute is dissolved in 50 gram of benzene. 50 gram of benzene. 50 gram of benzene. First one. The freezing point was lowered. Freezing point was lowered. Freezing point was lowered. All these are there in your text. Freezing point was lowered by 0.4 Kelvin. Kelvin. The unit given is Kelvin. The freezing point depression constant of benzene, freezing point depression constant of benzene, freezing point depression constant of benzene is 5.12 Kelvin kilogram per mole. Kilogram per mole. Find the molar mass of the solute. Find molar mass of the solute. Find molar mass of a solute. Find the molar mass of the solute. So this time we have to find out the molar mass. 1 gram of the solute plus 50 gram of benzene. The solvent is benzene. The solvent is benzene. 50 gram of benzene. Emmanuel, the solvent is benzene.
Yes, sir.
And the solute is unknown. Solute is unknown, but 1 gram of it. Then the freezing point of benzene was lowered by 0.4 Kelvin. Then the freezing point depression constant of benzene is 5.12 Kelvin kilogram per mole. What is the molar mass of the solute? Freezing point and molar mass. So what is the relation to be used to find out the molar mass? What is the equation? MB is equal to, you're right, 1000 kf into WB by delta TF into WA. You're right, at least the equations known to you. You will get some credit for the equation. Some credit will be given for the equation. You write that also. For physics and mathematics even. You write the relevant equations and formulas. There will be some credit for that. Okay. So we have to find out the MB freezing point. You substitute the values is equal to 1000 into what is Kf? Freezing point depression constant. That is given to be 5.12. 5.12 into what is mass of the solute, WB solute, that is equal to 1 gram by then delta TF, that depression of freezing point. Emmanuel, can you find out the depression of freezing point from the given data?
0.4 Kelvin.
Correct. It is correct. Yes, it is directly given. It is correct. 0.4 into WA, mass of the solvent in gram. It is given in gram 50. 50. Molecular mass, what is the unit? So much gram per mole. Or you can write U, unified mass. That is the unit. You simplify this. You simplify. On simplification, ഇപ്പോൾ നിങ്ങൾ ചെയ്യേണ്ട സാവധാനത്തിൽ നിങ്ങൾ സിംപ്ലിഫൈ ചെയ്താൽ മതി. You must simplify it yourself. Not to satisfy me, not to satisfy anybody else, but to satisfy yourself. You try it. ഒന്ന് ശ്രമിച്ചു നോക്ക്. ഇത് ബുദ്ധിമുട്ടൊന്നുമില്ല. 50 ഒക്കെ അല്ലേ, അത് അങ്ങോട്ടും ഇങ്ങോട്ടും ക്യാൻസൽ ചെയ്ത് പോകും. കിട്ടിയോ? Anybody has got it? Not from the directly from the text.
256.
You got it. 256. You got it or you got it from the text?
I got it.
From the text or you calculated?
Calculated.
Okay. 256 gram per mole. 256 gram per mole. Or you can write a 256 U. 256U. Okay, it's a problem. Similarly, we can draw a graph as in the previous case. We can draw a graph between the vapor pressure and temperature, freezing point. You draw that also. May not be asked for the examination. Just you write vapor pressure Vp along the y-axis and the temperature that is along the x-axis. You draw the graph. We are going to find out the freezing point, and then you'll get a graph like this. See, the nature of the graph, see, it will be like this, the graph. The nature of the graph. This is this part from here, from this bend. It is almost a straight line. The other portion that is curved, and that is the vapor pressure temperature graph for pure solvent. In the curved portion, see here, you may call this point A. Above point A, the curved portion, that is the liquid form of the solvent. Liquid solvent. Graph for solvent in the liquid form. Solvent in the liquid form. And this one, solvent in the solid form. Solid form. So the graph for the solvent in the solid form, in the book it is given the frozen form. Frozen form is the solid form. Frozen form is the solid form. Okay? Frozen means solid. And the other part is the liquid part. So we are, say from right to left, the temperature is lowered, decreased. Right to left, the temperature is decreased. So you start from the top end, and you move along the curve. At the point A, see here, at this point A, the liquid solvent begins to freeze, and that is the freezing point. Say, that is the freezing point. The point A, that is the freezing point. So this is the freezing point. Freezing point of the solvent. Freezing point of the solvent, that is P F 0. Freezing point of the solvent, P F 0. Freezing point of the solvent, P F 0. So at the point A, the solvent begins to freeze. The solvent begins to crystallize. So below that temperature, the solvent is in the frozen state, in the crystalline state, in the solid state. And that is the solid curve. Solvent in the solid form. That is the solid curve for the solvent. And above A, that is the solvent curve in the liquid form. Okay. Now you draw the curve for the solution. The solution is having lower vapor pressure. It is having lower vapor pressure. So the curve will be, see, it is like this. This is for the solution. For the solution, that is the solution curve. And at this point, what happens? Say at this point, there is a freezing of the solvent. corresponding to this temperature, the solution begins to freeze. Solution begins to freeze means the solvent begins to freeze. Only the solvent is freezing. The solute is in the solid state already. Solid is non-volatile, it is in the solid state, no doubt. There is no question of freezing the solute. Only the solvent is freezing. And at this point, we may call it as the point B. Point B. At the point B, the solution begins to freeze. And the temperature corresponding to that, that is the freezing point of the solution, TF. TF. And which is a lower value, TF or TF0. Emmanuel, from the graph, what do you feel? Is it a TF or a TF0, which is a lower value?
TF.
TF is a lower value. And what is TF? Freezing point of a
Solvent.
solution.
Solution.
Solution. Freezing point of a solution. So freezing point is depressed. There is lowering of a freezing point. Now you take this difference, and this difference will be delta, this difference. That is equal to delta TF. Delta TF. That is the difference in the freezing points of pure solvent and solution. That is delta TF. So we can get delta TF graphically like this also. I think that nobody is going to ask this question, and you just try to remember that. That's all. That is drawn. Finish. The vapor pressure, temperature graph. That is for freezing points. Freezing points. The freezing point, there is a slight difference compared to the boiling point curve. Do you remember that boiling point curve? Eh? Boiling point curve, see, it is like this. Boiling point curve. This is for solvent and this is for a solution. Solution. Here there is no break. In the solvent curve, there is no break. Similarly, in the solution curve, there is no break. But in the freezing point curve, there is break. Here there is a break. At A also, there is a break. Break is there. Okay. But for a boiling point, the curves are continuous. There is no break. That is slightly curved. That is right. But there is no break. But in the freezing point curve, there will be breaks at A and B. A corresponding to the freezing point of the solvent, and B corresponding to freezing point of the solution. Solution. So there is a break in the solution curve as well as in the solvent curve when we study the freezing points. But in the boiling point, there is no such a break. Do you follow, my dear friends?
Sir.
Just to compare both the curves. Just to compare. It is for the comparison I have given this. Both are vapor pressure temperature curves. Vapor pressure temperature curves. Solvent upper curve, solution lower curve. No doubt in that. Similar pattern. But in the boiling point curve, this is for a boiling point. In the boiling point curve, there is no break. But in the freezing point curve, there is break. Okay. So it finishes the third one, that is a depression of a freezing point. Now let us go to the last one, that is osmosis and osmotic pressure. So the fourth one, osmotic pressure. Osmosis and osmotic pressure. So first let us see what's meant by osmosis. Osmosis. Okay, to illustrate osmosis, we are studying the properties of the solutions, dilute solutions. Is it not? Eh? We study the properties of a dilute solutions. So osmotic pressure is also related to solution, properties of solution. Okay. So you take a system, a thistle funnel. As you know, I am an expert in drawing. Here there is a thistle funnel, long-tailed funnel, and here there is a that is open. That is inverted thistle funnel. Thistle funnel is like this. This is our thistle funnel. Okay, that one. Now this is inverted thistle funnel. Now this thistle funnel, this portion that is covered with, say, a membrane called a semi-permeable membrane. Semi-permeable membrane. Semi-permeable membrane covered with a semi-permeable membrane. For example, pig's bladder, pig, PIG itself. PIG, it's a natural semi-permeable membrane. It's a natural filter. That is a natural filter. Pig's bladder or a parchment paper, parchment paper, leather, parchment paper. That is also a semi-permeable membrane. So the question arises, what is a semi-permeable membrane? Say you can write afterwards, just wait. A semi-permeable membrane is one which will allow the passage of the solvent, not the solute particles. Only the solvent particles can move. Only solvent molecules can move through the fine pores of the membrane. Such a membrane is called a semi-permeable membrane. We can write the definition later. Just listen now. So a semi-permeable membrane is a membrane, a separation which allows the passage of solvent molecules only, not solute molecules or solute particles. Solute particles cannot pass through. So solute molecules cannot pass through the pores of the membrane. Only the solvent molecules can pass through the pores of the membrane. That is because the pores of the membrane are so fine, so small, so microtype, very small, so that only the solvent molecules can pass through that. Such a membrane is called a semi-permeable membrane. For example, a natural semi-permeable membrane is pig's bladder. Another one is a parchment paper. Parchment is leather. Parchment. Similarly, parchment then pig's bladder. Pig's bladder. These are semi-permeable membranes. Okay. The solvent molecules can pass through this. We can have, nowadays we can have the synthetic semi-permeable membranes also. A synthetic semi-permeable membrane, for example, cellophane membrane, a plastic material, plastic-like material, cellophane membrane. That is an artificial semi-permeable membrane. A synthetic semi-permeable membrane. Or a copper pot coated with a cupric ferrocyanide. Cupric ferrocyanide. Cupric ferrocyanide. You take a porous pot. Porous pot, manpatram is taken. A porous pot, kuja, for example, that is taken. Porous pot is taken. Clay, made of clay. It is porous. Fine holes are there. Hmm? And that is coated with a cupric ferrocyanide. So the membrane of a cupric ferrocyanide can act as an artificial semi-permeable membrane. Similarly, cellophane membrane that also can act as a semi-permeable membrane. Natural parchment, similarly pig's bladder. Anyhow, semi-permeable membrane will allow the passage of the solvent molecules only, not the solute molecules or solute particles. Okay. Now you do one thing. You take a thistle funnel, and it is covered with a semi-permeable membrane. For example, cellophane, artificial. Okay, it's all right. Now everything is artificial. So that is covered with a cellophane membrane, artificial semi-permeable membrane. Now you take a copper sulfate solution. Very carefully, carefully, you add copper sulfate solution into this. Say here, copper sulfate solution. What is the color of copper sulfate solution? You say, Emmanuel, what is the color of a copper sulfate solution?
Blue.
Eh? Copper sulfate solution. What is the color I have shown here?
Blue, blue, blue.
That is blue solution. Okay. Now this is the level of copper sulfate solution. Okay. Now this is kept, the thistle funnel filled with a copper sulfate solution that is kept in, say, a beaker. This is kept in a beaker containing water. Say, it is kept in a beaker containing water. There is water in this. There is water. That is the arrangement. And very carefully you wait there. Show some patience. You must show some patience and observe. Can see that slowly the copper sulfate level in the thistle funnel, it is slowly rising up. It is moving upward. It is slowly rising up. Follow what I say. And up to where? Up to a certain height. Up to a certain height, the copper sulfate solution level, that is arisen. That is going up. That is the new level. After reaching a certain head, a certain height, it remains stationary there. It remains there. There is no further, say, moving up. Okay. And what's the reason for rising up of the copper sulfate level? That is because the volume of the copper sulfate solution inside the thistle funnel is increased. How is the volume increased? The volume is increased due to the movement of water molecules through the semi-permeable membrane. Water molecules are moving through the semi-permeable membrane and it reaches the solution side. And that is why the volume of the solution inside the thistle funnel is increased and the solution level is rising up. And that continues only up to a certain height. After that, there is no rising up. It is stopped there. Okay. And there is the movement of the passage of water molecules, solvent molecules through the semi-permeable membrane. And this passage of solvent molecules, only solvent molecules through semi-permeable membrane from solvent to solution. Say, from solvent to solution, solvent to solution. That's called osmosis. We can write the definition. Just wait. Understand these two terms first. So the passage of, the movement of, the penetration of solvent molecules, only solvent molecules, through semi-permeable membrane from solvent to solution. That's called osmosis. That is called osmosis. Osmosis. And the membrane is called a semi-permeable membrane, which allows the passage of solvent molecules. Okay. Now, if we want, we can apply a pressure. We can apply a pressure on the side of the solution so as to prevent it, just to prevent osmosis. And that pressure is called the osmotic pressure. Osmotic pressure. If osmotic pressure is applied, we can keep the solution level constant. We can keep it a constant. There is no rising up of the solution level. There is no change for the solution level. So the minimum pressure to be applied on the side of the solution, the minimum pressure to be applied on the side of the solution just to prevent, just to prevent the process of osmosis, that is called osmotic pressure. So we have seen three terms here. Before winding up, let me just recollect the three terms. One is semi-permeable membrane. What is meant by semi-permeable membrane? You say, what is a semi-permeable membrane? What is it? Semi-permeable membrane. Nobody is there. Only two persons are here. Okay. A membrane which allows the passage of only solvent molecules. That is a semi-permeable membrane. Then osmosis. What is osmosis? The passage of solvent molecules from solvent to solution. We can write, wait. The passage of solvent from solvent to solution through semi-permeable membrane. That is called osmosis. Then osmotic pressure. That is the minimum pressure to be applied on the side of the solution, just to prevent osmosis. That is called osmotic pressure. So we have seen three terms. More details you can see in the coming class. Let me stop now. You go and have your lunch. Thank you.